We're doing scientific notation. Right, this is what standard form looks like. That's 3,500,000, also known as 3.5 million. If you ever hear that someone say that on the news or something like that, 3.5 million, that's what that looks like. It's 3,500,000. Okay, you'll hear 1.25 million. That's 1.25, which is 1,250,000. Scientific notation, okay, which you've seen before in science. Science and math go hand to hand. Okay, the more math you do, the more science you're going to do. Okay, science uses math almost a lot of, like calculus and trig and physics. They all go hand in hand. Right, the math problems in calculus and trig are based off of physics problems. Physics problems are based off math problems. You have to use numbers and that type of stuff. It goes hand in hand. Scientific notation, I know you've already seen it in science, so this should be just a review to you. All right, so please make sure you're paying attention, make sure you understand what we're doing. This is what 3.5 million looks like in scientific notation. 3.5 times 10 to the 6th power. How do I know it's the 6th power? What I've done is I've counted how many spaces I moved when I put the decimal here. I went 1, 2, 3, 4, 5, 6. I've went 6 decimal places to the left. I've made a large number smaller, and so it's 3.5 times 10 to the 6th. Your homework will ask you to express numbers in standard form. So they give you something like this, 2 times 10 to the 3rd power. So I always write the first number, right? And then I add decimal places. We start here at 2, and I'm going to add 3 decimal places. So how many zeros am I going to add? 3. All right. If you're adding decimal places and there's not a number already there, then you're going to add a 0. The reason we use scientific notation is to get rid of all these zeros. We call zeros insignificant numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are significant. Those change calculations. Those change when you're doing math problems. Those change your numbers. Zeros do not. So that's why we leave them off. They're considered insignificant. I'm going here. There's not any numbers behind 2, so I just add zeros. I add 3 zeros. Now here, okay, do I have 6 zeros here? No, because I had a number right behind the first number. You always put your decimal behind the first number. So even though I went 6 decimal places, I only had to add 5 zeros. All right, so do not think that since this is a 3, I always add 3 zeros. If there was a number here, if this was 2.1 times 10 to the 3rd, I'd only add 2 zeros. Make sure you're paying attention to that. Write these 2 numbers down. We have 6.8 times 10 to the 5th power. 6.8 times 10 to the 5th. Okay, I'm going to move the decimal 5 times. 1, 2, 3, 4, 5. So I'm going to add 4 zeros. And then there's my number. 680,000. Any questions? This 3.25 times 10 to the negative 4. When we have a negative exponent, we're going to the left. Right? Everything we've done so far had a positive exponent. We've always gone to the right. Since it's got a negative exponent, we go to the left. So we move 4 to the left. 1, 2, 3, 4. So that means I'm going to add 3 zeros to 3, 2, 5. And there's my number. They use scientific notation to either make large numbers smaller. We're talking about light speed. That's a huge number. When you're talking about the distance to like planets, those are huge numbers. Those are millions and billions of miles away. So they use scientific notation. It eliminates zeros, right, that are insignificant, that you don't need, and it also helps to clarify exactly how many decimal places. Someone can miscount a 0 and get numbers off. If you have 6.8 times 10 to the 5th, you don't get those numbers off. They also allow you to make small numbers larger. 0.000325 is not a number you want to read off all the time. 3.25 times 10 to the negative 4, that's an easier number to read. especially when you're doing calculations, and if you had an extra zero in there or you left off a zero because you miscounted, that wouldn't be good. So that's why scientists have come up with scientific notation. Write this down. Your homework's also going to say this: express the number in scientific form, making sure it's in scientific notation. We have 4 million. So what I do is I count where the decimal is now to where it needs to be, which is always behind the first number. Scientific notation is always behind the first number. So I have 4.0 times 10 to the what power? That's what I'm counting. 1, 2, 3, 4, 5, 6. Right? Make sure you always go from the where the decimal place is to where it needs to be. Whereas it's always behind the first number. Here it's right there. It needs to be right there between the 5 and the 8. Always behind the first number, the first significant number. All right, zeros are not significant. So I go 1, 2, 3. So this is 5.8 times 10 to the third power. Any questions so far? Here I have 0.072. So the decimal is going to end up there. And I count how many places I moved it, which is 2. So I've got 7.2 times 10. Then we have to decide, is this going to be the second power or the negative second power?
Negative.
It's going to be the negative second power. Because if I wrote this, which someone's going to do in their homework today, does that look like this? No, it looks like this. Is 720 the same thing as 0.072? No. So do not do that. If you're making a small number larger, then it's a negative exponent, which is 7.2 times 10 to the negative 2. All right, the problem for these two numbers goes like this. It says scientists estimate that there are 3.5 times 10 to the 6 ants per acre in the Amazon rainforest. 3.5 times 10 to the 6, which I already told you what 3.5 times 10 to the 6 is. It's 3.5 million.
Yeah.
3,500,000. That's per acre. Scientists also estimate that the Amazon rainforest is about 1 billion acres. Find out how many ants inhabit the Amazon rainforest. So they give you these two numbers. We're going to be timesing them. The easiest thing to do is separate these two numbers and multiply them. So do 3.5 times 1. And then we're going to be timesing the powers of 10, which is 10 to the 6th times 10 to the 9th. So you separate the numbers. Right? What's 3.5 times 1? 3.5 times 10 to the what power? Well, remember from last week, what do we do when we multiply bases? We add the exponents. What is 6 plus 9? 15. So there are 3.5 times 10 and 15 ants in the Amazon rainforest. It's not exactly that. That's a rough estimate. But that gives you a good idea.
I don't want to go in.
All right? Now, okay, make sure you're paying attention. This says write in scientific notation. Is this in scientific notation? Yes. Yes, it is. And we know it's in scientific notation because it has the first number with a decimal behind it. There's always a decimal in the first number. If you were to get something like this, what if your numbers worked out to this? 35 times 10 to the 15. Would that be scientific notation? No. So what I have to do is I'd have to move the decimal one time to make that 3.5, and then I would have to add to the exponent. Right? If I move it one time, I have 1. So make sure that your answer is in scientific notation. Sometimes you're lucky and it ends up like this. Sometimes you're not. And that means you got to be paying attention.
Is there going to be some of those on the homework?
Mm-hmm. Okay. Now, if I wanted to, just to give you an idea how many ants are in the rainforest, I could write this out. There would be 14 zeros there. It's a big number, isn't it? Write this down. They might give you another problem where you have to divide. Make sure you read the whole problem. Make sure you understand if you're multiplying or dividing. If you divide, we do the exact same thing where we split up those numbers and those numbers. So we do 8 divided by 4 times 10 to the 5th divided by 10 to the 4th. Which, what did we learn last week? If you're dividing bases, you do what? You subtract the exponent. 8 divided by 4 is 2. So 2 times 10 to the, what power, Beagle?
1.
1 power.
Yeah.
So I could leave it like this. Okay? Or I could go ahead and write it out as 20. Alright, if it says scientific notation, it'd be 2 times 10 to the 1 power, or 2 times 10. Right? 1 is understood, so you don't have to write it. Or if it says write in standard form, go 20. Alright? Any questions? Write all of this down. Geological time period. What they want you to do is they want you to compare time periods. Okay? They want to know ordering the time periods from oldest to youngest. Which was the oldest? What's the youngest? They want you to do that because they want you to have to look at the numbers and you figure out which one's the biggest. Alright? Which they've done here to mess with you. The biggest number you see probably, or the biggest number you think's up there is not. Right? If you were to go by the front numbers right here, you would think tertiary would be first. It's the oldest. It's got 6.64. But it's not. It's actually the youngest based off of exponents. So you always go off exponents first. Look for the biggest exponent. The biggest exponent's 8. So then what we do is then we look at the numbers in front of the ones that have an exponent of 8, which will be 2.08, 4.38, and 2.45. So the oldest is the Silurian time period. Because it is 4.38 times 10 to the 8, which is, if I remember right, 438 million years ago.
Wait, do we gotta say how many it is?
Nope, just says order of the time periods. So then next would be Triassic, because 2.45 is bigger than 2.08. Next would be Jurassic, because it's the only one left that has a power of 8. And it was 208 million years ago. And then you look at Tertiary. That Tertiary was youngest at 664 million years ago. So Tertiary is last. It's the youngest.
So on like the homework, most.
Here's your homework assignment.